All right, so in lesson 5, we're going to look at our next vector operation, which is called the dot product, which has some other names. Sometimes you'll hear inner product, and sometimes you'll hear scalar product. So I'm always going to use dot, but if you're reading online, some websites might use these other words, or some textbooks might use those other terms, but I'm always going to say dot. So I'm going to start with, to answer the question of what is dot product, I'm going to start with what it's not. So this lesson and the next lesson, we're going to learn two things that both have the word product in their name. So we have a dot product, which uses the dot symbol usually for multiplication. And we have what's called a cross product, which uses kind of what you would normally think of as the X multiplication symbol. So we're going to learn something called dot product. We're going to learn something called cross product. Even though they both have the word product in their name, they are not multiplication as you think of multiplication. So something like U, V with no symbol in between, like U times V, that doesn't exist. It's completely meaningless to write something like that. So you always need a symbol between them. One's for dot, one's for cross. There is no such thing, like neither of them will look like this, where you multiply the x's and multiply the y's. That's not a defined operation with vectors. It's completely meaningless. So they are different from what multiplication as you think of it. So even though it's got the word product in its name. So what dot product is, it's defined by this formula. The magnitude of u, so if you have two vectors, u dot v, you take the magnitude of u, you multiply it by the magnitude of v, and then you multiply that by the cosine of the angle between them. And specifically, when I say the angle between two vectors, it's always when they're drawn tail to tail. That's the tail to tail angle between the two vectors, because our default way to represent vectors is have them starting at the origin. So if they're both starting at the origin, they'd be drawn tail to tail. Theta would be the angle between the vectors there. So that's what we're going to define what dot product is. And notice that the magnitude of u, that's just a scalar, that's just a number. Magnitude of v, just a number. Cosine of the angle, just a number. So when you take u dot v, you're taking two vectors. This operation turns the answer into a scalar, just a number. It's a number times another number. So when you dot two vectors, your answer is a scalar, which is why it's sometimes called the scalar product. Why this formula? I think it's rooted in physics. Like I know dot product is used for the work formula. The work formula in physics is the force vector dotted with the displacement vector. I don't know exactly why this formula came to be. I know that it does all the things you want a dot product to do, which is a weird thing to say mathematically, because define it to be what you want it to be is kind of a weird thing to say. But vectors come up in all sorts of shapes and sizes, different from just these coordinate type vectors that we're dealing with. So even when the vectors are different kinds of objects that don't really look like what we're doing, this type of operation will be, a dot product will always have certain properties, and this formula gives you those properties, I guess, is a poor way of explaining it. So what we're going to do now is that's one formula for dot product. We're going to use that formula, so that's sort of the definition of what a dot product is. We're going to use that formula to get what that would look like if, say, we had the coordinate version of the vectors. So you had, say, a v1 and v2 for a vector v as sort of your x and y, a u1 and u2 as a vector, the x and y of vector u. We're going to try and build that formula using those coordinates so that maybe we don't have to calculate the magnitude. Maybe we don't have to figure out this angle between them. So I'm going to start with my vectors. So I'll call this u, and I'll call this v, and they're tail to tail, so that would be the angle theta. And v is going to be, again, the vector v1, v2. U is going to be the vector u1, u2, so that's just sort of the coordinate version of this. And what I'm going to do is I'm going to complete kind of a triangle here. So I'm going to draw a vector that goes between those. And maybe I'll draw the arrow on that end because I need to give it some direction. So if I'm going to make it a vector, I'll make it look like that. So that vector, if we look at it, the starting ones are drawn tail to tail, and we're connecting we're connecting the two endpoints sort of. So that is a subtraction vector, and that is the vector u subtract v because it's going from v to u the way that I did that. So using coordinates, it would be u1 minus v1 and u2 minus v2. I'd subtract the x's, I'd subtract the y's. And the reason why I've done that is this makes a triangle. We've got formulas for triangles, and maybe this vector, the formula for dot product has a cosine vector in it. So maybe I would write out the cosine law formula, which would be c squared equals a squared plus b squared minus 2ab cosine of c. And I'll write that out with those vectors in that picture, just basically with the hope that cosine theta is now in it, and maybe we'll be able to get the dot product. So c would be the side across from the angle, which would be the magnitude of u subtract v, would be the magnitude of that subtraction vector, because that would be this side in the picture. The a and the b would be the magnitude of u and the magnitude of v. And then minus 2, I'm going to squeeze this in. Actually, I don't have to squeeze it in. My page has no limits. And so that's what cosine law looks like with using the vectors on that triangle that we've made. And the wonderful thing that pops up there is that this is now sitting on our page, and that is the definition of what a dot product is. And so what I can do now is rearrange and find, get u dot v by itself. So if I rearrange that mess, I'm going to and these should have squareds on it, sorry. Those ones are all squared in the formula. Sorry about that. So I'm going to whoosh that over to the other side, make it positive 2u times v, whoosh the magnitude of u minus v. Oh my goodness, this is going great. And then divide by 2. So that's just the formula above, sort of rearranged for u dot v by itself. And now what's wonderful is I can do the magnitude of u. It would be the square root of its component squared, and we've got magnitude of u squared. So that square root's going to go away in a second. Magnitude of v would be the square root of its component squared. So v1 squared plus v2 squared. And then subtract u1 minus, so its component squared. So that's the vector u minus v. So that's this vector here, squaring those components. So we get that divided by 2. And this turns into a great big awful mess, but basically the square root's going to cancel out with the squared, so that first part just becomes u1 squared plus u2 squared. The second one becomes v1 squared plus v2 squared, square root goes away. And then I'm going to subtract, and in brackets, so that was the magnitude of u minus v all squared. So again, the squared and the square root cancels each other out. And then I'm just going to expand these two brackets. So I'm going to get u1 squared minus 2 u1 v1s plus v1 squared. So that's the first bracket expanded. Remember, it's u1, it's this multiplied by itself. And you have to do the full expansion. That's where the minus 2 u1 v1 came from. And same sort of thing, u2 squared minus 2 u2 v2. And then it's going to be a plus v2 squared. And this looks like a total mess. But now, u1 squared, there's a subtract u1 squared, that's going to go away. u2 squared, there's a subtract u2 squared, that's going to go away. v1 squared, there's a subtract v1 squared. v2 squared, there's a subtract v2 squared. So that all goes away. And what I'm left with is I'm going to pass this minus sign through and get positive 2 u1 u2, positive 2 u2 v2s, and then divide by 2. And that 2 factors out and cancels out both of those 2's. And we get this wonderful formula, which basically says the dot product of two vectors, you absolutely can do their magnitudes multiplied together and then multiply by the cosine of the angle between them. But if you know what those vectors look like with coordinates, you'll get the exact same answer if you take their x values, multiply them, and take their y values and multiply them, and add up those two answers. You'll get the same thing as doing magnitude of one times magnitude of the other times the cosine of the angle between them. And you don't need to know their magnitudes. You don't need to know the angle between them, which is usually the tougher thing to find in order to get the dot product. So that's a quick way to calculate it. So all of that was to get down to that formula there. So I'm just going to go over some properties of the dot product because they're important. So if you ever have a vector dotted with itself, so picture this as a dot a, you get magnitude of a times magnitude of a times the cosine of the angle between them. Well, the angle between a and a is 0. The cos of 0 is just 1. So you just get magnitude of a times magnitude of a. You get the magnitude of that vector squared. If you look at either version of the formula, you'll see that it is in fact the same forwards and backwards, so that dot product is a commutative operation is the fancy math word for that, but it is the same forwards and backwards. Again, important to keep these things in mind because not everything will be the same forwards and backwards. Dot product distributes over vector addition, so if you are adding two vectors and then dotting it with a, you can dot a with each of the separate answers and then add up their two answers. Now this formula is kind of just paying attention to what's going on. B plus C, that plus sign means vector addition. It means draw those two vectors head to tail and connect from the start to the finish. A dot B and A dot C, those are numbers. So this just means regular addition. Add up those two numbers. So the add sign in there is talking about two separate operations based on what's on either side of that addition sign. But the basics is the same. If you add up the vectors first and then do dot product, you'll get the same answer if you do two dot products separately and add up those answers. This one's just showing if you have a constant multiplied by the answer. So this is just regular multiplication on the left side, a number times a number. You'll get the same answer if you multiply that constant into either one of the starting vectors and then dotting it. So not to both, just to one of them. Okay, so I guess maybe I'll make note of this, maybe up here. So dot product can be different signs based on only the angle, because magnitudes are always positive, but cosine can be positive, can be negative, depending on that. So if we think about our cast rule, our angles are only going to be between 0 and 180, because if the angle's bigger than 180, well, then you're just measuring it the wrong way. You'll find an angle between the two vectors will always be less than 180. So if the angle is between 0 and 90, cosine is positive, and so the dot product is positive. If the vector is bigger than 90 but smaller than 180, if the angle between them is obtuse, you'll fall into the second quadrant where cos is negative. And so since the magnitude 0 is positive, cos is the only thing that can make it negative. So if your dot product's negative, it means the angle's obtuse. If your dot product is positive, it means the angle's acute. So if that's positive, theta is acute. If this is negative, theta is obtuse. And the last option, if the dot product comes out exactly 0, it means that those two vectors are perpendicular because cosine of 90 is 0. So that's the only way to make the dot product 0 is if the cosine thing is 0. So if you get an answer of 0, it means those vectors are perpendicular. So that's probably the most useful version. So that's the sort of, when I think about when dot product comes up, that's what I think of quite often is if you dot two vectors, if you get 0, they're perpendicular vectors. So you can quickly check if vectors are perpendicular, but often the question will be like, part of a vector, there's still some, variable in the vector, and you have to find what value makes it perpendicular to another vector. Well, then you'll set the dot product to equal to 0 and then solve for that missing piece of the vector. So if you want to make two vectors perpendicular, you set their dot product equal to 0 and figure it out from there. So we have these two vectors. We're going to use dot product to quickly decide which type of angles between them. So for this, u dotted with v. The quick way is you take the x's and multiply them, and then add it with the y's multiplied. And I get 50, take away 6, I get 44. So x times x, y times y, and add them up. I get 44. That's a positive. Therefore, the angle is acute if the dot product is positive. Now for part B, if we don't want to know just what type, if we want to find the actual angle, we have to actually work with the other version of the formula. Magnitude of u, magnitude of v times the cosine of the angle between them. So the difference here is we found the dot product using the coordinates, not using the angle. So we know the answer's got to be 44. We can do the magnitude of u. It's going to be the square root of 5 squared plus 6 squared. We can do the magnitude of v. It's going to be the square root of 10 squared plus negative 1 squared. And then the only variable left in there is cosine of theta. So in order to rearrange for cos theta, we're going to divide out those two square roots. So 5 squared plus 6 squared is 25 and 36, so the root of 61. And then the other one's the root of 101. I can now divide those out. And get, so this fraction, when I punch it in, I get 0.560, let's say that, and then do the inverse cos of that. My calculator's in radians, so it's 0.97 radians. So multiply by 180 and divide by pi. Should get 55.9 degrees if I was in the right mode, so I'm going to round that off to 56 degrees. I'm going to switch my calculator to degrees if I know how to do that on this one. There we go. Okay, so I should get an angle of 56 between those vectors. All right, so now we're going to step into 3D. And I could go through that whole process and prove the formula for dot product. So the overall formula is the same. It's still u dot v equals magnitude of u, magnitude of v times the angle between the vectors. I could go through this exact same process. I could even draw the picture as like a 2D representation of the 3D vectors. But basically all that's going to happen is you're going to get a third coordinate in each of these, a third coordinate in each of these, and then you end up with just the formula at the end is multiply the x's, multiply the y's, and then add on multiplying the z's together. So I'm not going to go through all that. The formula works exactly the same in 2D as it does in 3D. So for A, again, if you want to pause this and go through A and B quickly and then unpause and make sure you get the same answer as me, by all means. So U dot V is going to be 15, so that's 3 times 5. 6 times 17 is 102, so subtract 102 because that's negative. And then 9 times 4 is 36. I don't know why I punched that in, but I did. And I can see I'm going to see that that's going to be negative, so let's get the actual answer though, because we'll need it for part B. So it's negative 51. And since that's negative, we know theta is an obtuse angle. And then part B is going to work pretty much exactly the same. We're going to start with the sort of definition formula. And we're going to solve for theta. So we know the answer is negative 51. Magnitude of U is 3 squared plus 6 squared plus 9 squared in a square root. Magnitude of V is 5 squared plus 17, negative 17 squared, but the negative is going to go away anyway, so I just won't even write it, times the cosine of theta. So cos theta is going to be negative 51, 9 plus 36 plus 81, divide by the root of 126, and then also divide by the root of 330. So I got negative 0.25 basically when I did that, and then when I do the inverse cosine, I get around 104 degrees if we round off to a whole number of degrees. I get 104.48, so depending on how many decimals you put it, you might have it rounding up to 105, but I'm not too worried about it. Okay, and then for this last one, again, I kind of gave a hint when I talked about what dot product's useful for, so see if you can take an attempt at this. But this vector, 2, 4, minus 2, is supposed to be perpendicular to x, negative 3, 4. Wants you to solve for the value of x. So the idea here, if vectors are perpendicular, then their dot product will equal 0. And so what that's going to look like is multiply the x's, so 2x, multiply the y's, negative 12, and multiply the z's, negative 8, and that should equal 0. So we're adding up all those results. So that means 2x needs to equal 20 when I move over the negative 20, so x has to be 10. So that will be the value that works for that. Okay, so you've got a formula sheet going, I hope. I want you to add in both the definition answer, definition formula for dot product, and the two versions using the coordinates 1 in 2D, 1 in 3D, and then also put this note that the angle between two vectors is always the tail-to-tail angle, the angle when they're drawn tail-to-tail, and then there's some practice that we can work on in class.